This channel is devoted to honest investigations of science. I like to focus on everyday science and the way that everyday people interact with science and experience the ideas of science communicated to them in their lives. I invite people from the community, if you have questions about any topic of science, particularly if you have observed something that seems contradictory to the established science, or if there's something in the established science that appears to be contradictory with itself, please do come on down, drop a comment right down in there, and we'll see if we can help you out. Today's topics come from a YouTuber who goes by the name of Alan. Alan's been looking into gravity, and he is honestly quite skeptical about the modern theories of gravity and space and the round shape of the Earth. So that's okay, Alan. You are welcome here, and don't worry, I am not trying to change your mind. I'm not with the thought police, at least about all of those things. Remain skeptical, think what you're going to think. My hope, though, is that by going through your point of view and contrasting it with the way I think about science, I might inspire you to think of science in a more friendly way than I think you currently do. Alan starts us off with some links to some nasa.gov websites. Many of these are educational outreach websites appropriate for grades 5 through 12. So good material. These are good reading. This tells us what Alan's been reading, and also for any of you who might have questions about what this is all about. These are good links. I will put them down in the description right there so you can just follow those links. You don't have to read them off the screen. Okay, let's start off point by point going through Alan's summary of gravity as he has understood it after reading that material. First off, an object's mass determines its gravitational force. I say, yeah, that's a very good summary of it. We would say that the amount of attraction that a mass feels to any other body is dependent on how much mass the object has. Yes, that's true. What's next? Alan says that force is so strong that it bends space-time around it. Now, I'm not going to say that's wrong, but it is worded very oddly. I would say that the force is not bending space-time. What I would say is that Einstein's method of describing gravity, which is pretty complicated mathematical stuff that honestly, let's not dig into it. Let's just describe it. What Einstein has written with his mathematical expressions says that the presence of a mass will bend space-time, and that this bent space-time is what results in the gravitational force that we observe. So the main difference, I would say, between the way you phrased it and the way I would phrase it is that mass bends space-time, and that results in the force of gravity. Not that the force of gravity caused a bend of space-time, but you know, those are similar enough that it seems like you're on the right page. And I would further stress that if we're in the world of trying to grasp gravity, trying to comprehend gravity and apply the meaning of gravity, we should not jump straight into Einstein. Einstein's equations are hard. They are for very fine details that I think we should cover the basics before we dig into the complicated. And for the basics, I would always say, let's start with Newton's gravity. Newton's conception of what gravity was should get us through all of these conversations first, and then maybe we could talk about what Einstein brought to the table. Alan goes on to say, when another celestial body comes in contact with this bending of space-time, it can form an orbit if the following conditions are met. The celestial body's momentum, gravitational force, and its bending of space-time all have to be in perfect balance with each other as they pass by each other for the smaller one to get caught in an orbit with the larger celestial body. The first thing I want to point out is that gravity is not a contact force. Gravity does not have, the accepted description of gravity does not have a limit at which there's no longer a force of attraction between the objects. The force of attraction is described as being much greater as the objects are close and much smaller as the objects get farther away. And at what distance does it finally reach zero? The answer is never. It doesn't ever go to zero. They just get smaller and smaller and smaller as the objects get farther away. And so there's not like a moment as the comet is flying past, there's not a moment when it suddenly is being influenced by gravity. It's being influenced by gravity the entire time. It's just as it gets closer, the influence increases. Okay. So then we say it can form an orbit if the following conditions are met. Here's the conditions, and there's these three things listed that have to be in sync. Let me point out that this is only two things, because gravitational force and bent space-time are in fact one thing. They are, bent space-time is Einstein's description of how the gravitational force is created. That those are not separate. That's just one thing. Having reduced that, now we have momentum and gravitational force have to be in balance in order to get this perfect orbit, or in fact get a capture. Now, because there is no limit, it's not a contact force, there's no distance at which this begins, any pair of objects are technically in an orbit already. They are already in orbits. It might not be obvious because the distances are so great and the forces are so small that you won't notice any kind of orbit from that. The objects that are closer together and have larger forces have orbits that we can see, and that's what we're really talking about. The conditions, as in the matchup between momentum and gravitational force, determines not whether there will be an orbit, but what sort of orbit you're going to get. You can get lots of different types of orbits. You're probably thinking of perfectly circular orbits, which you need a perfect balance between momentum and gravity in order to get that perfect circular orbit. What happens if you don't have the right balance? If you don't have the right balance, you're going to get an elliptical orbit or even hyperbolic orbit. A hyperbolic orbit is an orbit that doesn't come back. It just means a deflection. It just means you're coming at the massive object and you swing past it, you deflect a little and you're off and never to return. So we still call that an orbit that is a hyperbolic orbit. It's one of the types of orbits. So yes, the conditions have to be very precise to get a circle. But if they are not precise, you just end up with something that is not a circle. All right, what else have I got to say here? You talk about getting caught in an orbit that a small body gets caught in an orbit around a large body. And the truth is that is extraordinarily rare, and it cannot happen as you've described. In order to make it happen, you need the stars to align in just the right way, because you're going to need something else. You need a third body or some kind of interaction besides just gravity. Gravity cannot by itself capture an object into orbit. And that's, we could get into orbits all day, and it is pretty interesting. But let's start with that, which is, I see a misconception here, is the idea of a small body is caught in an orbit with the larger body is not actually something that really happens very often. We believe it does happen, but that's not the general case. The general case you're thinking is, well, then how did this moon get here? how did we get caught by the sun's, how did Earth get caught by the sun's gravity? It didn't get caught by the sun's gravity. It was formed already in this location, more or less. I mean, it has drifted over time, but the actual theory of how planets and stars form is that they come together from a cloud of dust that sort of clumps up, just like the dust in your keyboard clumps up for the most part. They clump up together, and then as that happens, two clumps, a small clump and a big clump, they're already in orbit. They are in orbit when they form in the first place. You might ask, where are all these non-circular orbits you're talking about? Let me show you an example. This is a handful of known objects, known comets and asteroids, just a handful of them that are known that exist within our solar system. And in here you'll see the major planets. There's Mars is in the middle there, and there's Earth's down in the inside. And here are these very almost perfectly circular orbits for the larger bodies that we find. And then you'll notice that Pluto is the white ring, which isn't circular. And then some of these others just that are absolutely crazy and out there. And this doesn't even show the more extreme comets, the ones that we see, like Halley's Comet, Hale-Bopp Comet, the ones that only come around once in a while. They do that because they're on extremely elliptical orbits, orbits that are super not circular. So there's a link there. I will make sure that one's down in the description as well, if you want to go and look at that. So Alan goes on to say, additionally, this happens in such a way that the orbits are on a flat plane. Yes, very much. The typical disk shape is the natural outcome of what I was describing of how we believe planets and solar systems form. We think that what happens is you start off with just a ball of dust, just a ball of gas and dust, just going every which way. And gravity slowly pulls it towards each other. Everything is being pulled together. But because of this thing that I was saying before, is that all objects are always in an orbit, right? So it's just going every which way. And every little particle, imagine every little particle in the cloud is in orbit around the center of the cloud. That's what you're going to get. So you'll get very elliptical orbits for some particles, very round orbits for maybe some particles in the middle, but it doesn't start as a disk. It starts just as particles orbiting every different direction. And then if you think about what's going to happen with that, as the orbits of these little particles carry them across the orbit of another particle, they can collide. If two orbits are not parallel, if they're all in a ring, they'll all be parallel, they won't collide. But if they are, one's this way, one's that way, then every time they go around, they have a chance to bump into each other. And when they bump into each other, they transfer momentum from one to another. And as that happens, and they clump up, as that happens, the momentum gets averaged out of all of these different things. We start averaging out the momentum of the various particles. And what you get left with is the average momentum of the cloud becomes the dominant momentum of the balls that get left behind. And so typically we would expect to find a central star and possibly other stars or planets in orbit, all moving in the same direction, swirling around at the speed that is the average rotation rate of the original cloud. If you take all the different speeds of all the different particles of the original cloud, you average them all out, that's the angular momentum you get in the final piece, and that average will be a disk. You can't have an orbit that goes like this, like around the sun. You can't orbit it up here. If you're up above, you have to orbit around like so, and that's going to keep making you cross through the plane, we call it the plane of the ecliptic, the plane where the other bodies are rotating. And each time you cross, there's a chance of a collision or a deflection, and you'll transfer momentum and get averaged in to ultimately to the disk shape. The disk shape is really the only thing that's long-term stable. On to Ellen's first question. My first question isn't even for a scientific explanation, it's for your personal opinion. If my understanding is correct, does it make any logical sense to you that this kind of uniformity could exist in such a way that it actually makes the celestial objects in the sky an accurate clock that you can use to navigate or tell what season you're in, when to plant crops, and when to harvest? Okay, good question, good observations. I just described swirling clouds of dust that eventually turned into planets going around a star, and I said that it is the natural conclusion that if you started with a swirling cloud of dust, that you would get orbits going around the central star, that's perfectly normal and expected. But is it normal to imagine that we would end up with this regular clockwork type of behavior? Let's start with this. The first thing I want you to understand is in this model, what we're saying is that the Earth goes around the sun. The other planets go around the sun, and the moon goes around the Earth. For a human being trying to figure out when to plant the crops, we can consider that for all intents and purposes, the sun is holding still and we are going around it. So if we look up at the night sky day after day, year after year, we will see that for the most part, the only things that move are the moon and the planets. Everything else is just holding still, and it is we who are moving. Now, why is that critical? That is critical to understanding this because that's why everything moves together in perfect unison. It is very hard for me to imagine that all the stars in the night sky move together in a perfect rotational clockwork motion unless we realize they aren't moving, it's us who are moving. Of course, it moves in a perfect clockwork motion because all that we're seeing is us rotating at a steady rate. And shouldn't we rotate at a steady rate? Yes, all predictions based on understood science would say that we should be at a very steady rate. Yes, everything must move like clockwork. And in fact, let me posit to you, does it make sense to you that all of these things in the heavens move in unison, in perfect clockwork motion, while we hold still? That we're not moving, but literally everything else is moving in perfect unison. That seems rather odd to me. Okay, keep in mind that the level of precision the sky clock can be used for, and we're supposed to believe that's all my chance from an explosion out of nothing. I think that's all by chance from an explosion out of nothing. Okay. First of all, Big Bang cosmology is taking things way deeper than I think we need to go in order to investigate what affects us in our daily lives. But yes, the talking about the Big Bang is very much something that science communication reaches individuals, everyday people, and that's something that they deal with, and it is something that is difficult to deal with. How are we supposed to take that? Is there an explosion out of nothing? I don't really want to go there. The fact of the matter is, science today does not officially know what happened at that time. We do not know, and we do not claim to know. Was it an explosion out of nothing? We don't know. Could it have been? There are theories that suggest that it was, but there are also many theories that suggest that it was not. We don't know that. It's active research that science is looking at. On the precision of the sky clock, let me reiterate. The entire model can be described like this. The Earth rotates once a day. So every 24 hours, we rotate. So that makes the sky clock go around in perfect unison. We don't have a billion different stars that are all moving according to some choreographed motion individually. They are just doing their thing. Everything's out doing its thing, and most of those are so far away that we don't notice them moving at all. Us talking regular, everyday, plant your crops type of talking, they just sit there. So we're spinning, and that makes them all move in unison. And if that were the case, again, think about this, the model, just think about the model as it stands. If that were the case, that we were spinning, could it be any way other than all the stars must move together by clockwork? If you accept that we are rotating, the stars must move like a clock. On the other hand, if we are stationary, why do you think the stars move in unison like that? The other thing that happens is the seasons, and that comes from the Earth going around the sun once a year. And again, if you start from a premise of, okay, let's say gravity is a thing. Let's say gravity exists. What would happen? This is what would happen, and that matches what we see, so we're happy with it. Again, we're going around once a year, and there's nothing able to speed us up or slow us down, so we have to stay at that same rate. Nothing we can do about it. Regular as clockwork, and that's what the model says is what we're doing. And you don't even have to answer this question. I'd like to hear your thoughts on it, though. I realize this question is more philosophical than scientific, so we don't give a scientific answer to it. I would actually say, no, this is a highly scientific question because it starts from the understanding of what the model really says. And so the model says we rotate once per day, and that gives the stars their regular clockwork motion in a swirl. And that the Earth revolves around the sun once per year, and that gives the regular clockwork motions throughout the year. And so because of that, this kind of uniformity is simply the natural outcome of the model and is not at all hard to believe based on this model. This model is not asking you to imagine some incredible coincidence took place that caused the stars to move in this perfect clockwork motion. No, the model says simply that the Earth rotates. Because it's rotating, the stars have no choice but to move in perfect clockwork motion. Question number 2. I'm assuming you're familiar with a coin vortex. Yes, I'm familiar with that. Would you agree that a coin traveling around a coin vortex is a good visual representation of what's being alleged in the links I posted above? Yeah, I would call that a pretty decent approximation of an orbit. Like when you drop the coin, it goes around and around and around, and we see an orbit, yeah. Where the simulation falls short is that the coin going around the vortex is subject to various types of friction, energy loss. Energy is lost as that coin goes round and around, and it slows it down. And that is something that orbits will not do. So let's jump here to this YouTube video that, again, I will link down in the description for you to watch. Let's watch a coin vortex in action. So, if that makes sense and is a good comparison, then would it also be fair to say, if the coin never gradually moved to the center and falls through the hole, that the reason it doesn't continue to be attracted to the Earth is because dark matter and dark energy? No. The coin falls into the center due to friction. And I put friction in quotes there. I'm saying that as the coin rolls, it is moving through the air and having losing energy to pushing the air out of the way. It's also making noise as it's in contact with the material. You hear it rolling. That noise is an energy loss that is being lost from the coin. So as the coin loses energy as it goes down, it falls into a lower and lower orbit. This doesn't have anything at all to do with dark matter or dark energy at all. No. Dark matter is something we'll get into, I think, later in your questions. Dark energy is something else entirely that is talking about the expansion of the universe, which is a whole nother topic. The Earth does not fall into the sun because there's no friction in space. Orbits have very little, very, very little. We usually just say zero. It's essentially zero friction. Okay, we can see what happens on Earth when an object travels around a curve like that. But they're saying that if you get the right speed and mass, that coin will just travel continually around the same spot. I would say, I don't know who they are. I can't speak for they, but I am saying that the reason the coin falls is because it's losing energy. The reason that an orbit does not fall or decay, the reason an orbit does not decay is because it is not losing energy, because space is empty. There's no drag, there's no friction, there's no sound. You're not losing energy to all of those things. Now, if you're in a very low orbit, like a low Earth orbit, our satellites, they are brushing with the upper parts of the atmosphere, and they're experiencing a small amount of friction. So they slowly decay. So you'll hear about an orbit that slowly decays. And that means the satellite is slowly falling closer and closer to the Earth, just like the coin does. Yeah, no friction in space is the simple answer there. And just imagine a model globe over the coin vortex, if that helps make sense of what I'm saying, if it didn't make sense. I can try some clips and images, yeah. No, I think it's perfectly clear, the idea, or at least it is to me. If anybody out there in comment land doesn't understand what we're talking about, by all means, we can clarify that. For question number 3, let's get into dark matter. They're saying in the 1930s, some guy observed a phenomena that defies the entire model they used to measure celestial body size, distance, and mass. Yes, you're talking about Fritz Zwicky. Fritz Zwicky was doing some measurements, and sure enough, the model, particularly the model at the time of gravity, the one that we are talking about right now, made some predictions about how fast celestial bodies should move. And according to Zwicky's measurements, those did not match. This left the scientific community with really 3 options. Option number 1, Fritz botched it and his measurements were all wrong. Or option number 2, the model itself is all wrong. Or option number 3, that the model was correct, but there was some mass that Fritz just couldn't see in his observations. First, your first knee-jerk is, hey, let's check that this Fritz Zwicky guy is right about his measurements. And so that's the first thing that scientists do. They rush out to duplicate his efforts and see if they can find out whether he did a good job or not. So over the years that followed, they agreed that, yeah, he had done this correctly. Many, many people afterwards confirmed that, yeah, according to every calculation we can do, every measurement we can take, that large celestial bodies do not move according to the mass that we can see. And so the next best guess is, well, since this model seems good everywhere else that we can test the model, that suggests perhaps there is just some mass that we cannot see. And thus was born the name dark matter. It's dark because we can't see it. It is matter because it appears to have a gravitational pull. And so that's what happened. Yeah, that is absolutely a good description of Fritz Zwicky and his discovery there. This guy then proposes that the cause must be from an invisible source, and that the invisible mass's gravitational force is acting on the celestial body, and that explains the anomaly. Yeah, that's pretty much, yeah, I'd say that's fair. I don't think anyone would be so foolish as to say that it was proven, but yes, he proposed that, and it seems like a very logical explanation for what we're seeing. We are seeing an apparent gravitational force that does not match the model unless there is some mass that we cannot see. And so that's exactly what he thought. And let me just digress for a moment and tell you the story of Neptune, or, you know, I don't want to take forever with this. I want to tell you to go look up the story of the discovery of the planet Neptune, that's exactly how it was discovered in the first place. Was according to the model of gravity, the behavior of the planet Uranus was odd. It did not correctly match the model unless there was a mass out there beyond it. And they did some calculations and they determined, well, if the model is correct, there must be a planet right around here. So then they go out and they look and they're like, hey, you mean this planet? Sure enough, there's planets waiting for you right there. And so the pattern was well established, that the idea of if there's just something you can't see that would solve this problem, then let's go look for it. And that is exactly what people have been doing ever since. So then you say, 40 years later, in the 70s, another guy observes another anomaly, and because of that observation, the notion of dark matter is firmly established. Let's give a little shout out to all the science ladies out there, because this other guy you're talking about is none other than Vera Rubin. Your description of how this went down is, yeah, it's pretty fair. First, Fritz Zwicky does a measurement and proposes, it looks like there's something going on here. Vera Rubin, many years later, comes around and discovers the same thing in a different way, completely different way of observing the night sky. She discovers indeed confirmation that yes, we're seeing this also in another place. And so at this point, it's been many decades since the original discoveries, and we have confirmation of a second type of observation, and this now seems pretty solid. This is not an error, because we have two different ways of observing this phenomenon. The notion of dark matter is firmly established. What exactly that is, though, has not yet been established, and it is still not established. Dark matter is merely the name for the phenomenon that these scientists were describing from real-world observations, and many notions of what that could be. And it continues on to say things like, in many ways, scientists know more about what dark matter is not, though they do have a few ideas about what it could be. Right, that's, yeah, I would agree with that. We know that the way objects move, particularly very large objects, galaxies rotate at a particular speed, that if you punch in those orbital calculations that we're talking about with the amount of gravitational force and the momentum of the various stars, it doesn't match the model. So either we're going to say the model is incorrect, or there is some source of gravitational force that we cannot see. So early notions included maybe there were very dark objects. They were black holes or dark brown dwarf stars that are not bright enough to see, other just bodies in there that we just cannot see. But many experiments were done to look for those, and it seems like that is not the answer. We have more or less ruled that one out. Other ideas include modifying the model of gravity to say, okay, gravity, the model that exists now is not quite correct. There's something wrong with it that does not account for these very, very large sizes, these very large distances. Maybe gravity is stronger at large distances than we are currently giving it credit for. And so there are many people working on that idea. I think my own personal opinion is that we're going to discover a type of, we'll call it matter. It's not matter that we understand, that we see and we touch. It is something else. It is a particle made of particles that interacts with gravity, but does not interact in essentially any other way. Maybe it does not interact at all in any other way. And that is what I think most people think of when they think of dark matter. There is some pretty good evidence that may be the case. And maybe we're going to see that in some coming slides. We could talk about it. It's interesting. Ultimately, what you're really talking about, what you're really questioning is the method of science that people have used throughout the years to come to these speculative conclusions. We are definitely in the speculative area of science with the concept of dark matter. It's not a done deal. We don't know. What we are talking about is that scientists have made observations, they have taken precise measurements, and they have applied the existing model and discovered that the model leaves something incomplete. There's something more to learn, and that is what dark matter is. Dark matter represents scientists' effort to learn more about the world around us. Question number 4, measurement. It appears like any time they make an observation that goes against established model they have, they invent a new theory to back it up, and then 30 to 40 years later, they confirm the theory with another observation. Yeah, I would say I think you just described science. Let's look at this philosopher of science, Thomas Kuhn, who is very influential. Here's his book. Here's a link that I'm going to put down in the description for you where you can read a summary of what Thomas Kuhn says. Thomas Kuhn is pretty influential because he explained pretty well what we see as a pattern of how science and science history has taken place over the generations. Many people agree with Thomas Kuhn's analysis, and I agree with it as well. The summary of that is that science moves in paradigms. That at first, some scientist makes a discovery, they announce the discovery, and everyone is at first quite skeptical of crackpot Doc Brown and his DeLorean, right? At first, the scientist is a crackpot. And then after a while, people check the work of the scientist and they discover, lo and behold, they were onto something all along. And then this thing about they confirm the theory with another observation. Well, every generation or so, some new technology emerges and that allows us to make a different kind of observation. And new people are constantly thinking and trying things, trying different things. And so we, as human beings, we amass a body of knowledge over the years, and we learn from those who came before us. So Newton described this as standing on the shoulders of giants. What that means is we take everything that the people before us learned, we add more to it, and now we're able to learn something new that they were not able to see. When you have a single observation of something odd, the community remains somewhat skeptical of that. If you can confirm that observation with a completely independent observation, now that is something that gives us all good reason to be convinced, I think you're really on to something with that. And that is what causes the paradigm shift. Okay, this happened to Newton with Bentley's paradox. His response to why the universe didn't collapse in on itself was because God must make constant corrections. Okay, yeah, we call that the God of the gaps. And honestly, Newton was guilty of this. The phrase, the God of the gaps, a very old phrase that describes the concept of when you have a gap in your understanding that you might be tempted to just say, oh, well, that's just God. That's God doing that. That's the hand of God there. And usually this is used as sort of a derogatory type of philosophy. And the reason for that is because we understand that over the years and the decades, we're going to fill in those gaps. That historically we have slowly filled in more and more of those gaps. If your idea of God lives in those gaps, then you're going to find that God is being chiseled away over the years because those gaps are being filled in. And so I think that a much better source of spiritual enlightenment is to see the hand of God not at work in the gaps, but in the brilliance and the wonder of everything out there. The things that we understand, the beauty that is the gravitational constant, the beauty that is these orbits, and how such a simple set of rules, the Newton's laws just by themselves, lead to the existence of these planets and these solar systems, I find very beautiful and very amazing. If you're looking for a creator, there it is. The hand of the creator is right there in those laws. So no fancy math formula for that one, no new measurements, no adjustments, just involve a divine creator as needed. So he invokes a creator, but then says that creator made a mistake that he constantly has to correct. And Newton, a man not a divine creator, noticed a flaw in this creator's work. Now, Newton was a very religious man, a Christian. I do not think that Newton was ever critical of the divine creator or the creator's work. My interpretation of Newton's statements from what I have read of those was that he was very much falling into the God of the gaps mentality, that Newton was aware of things that he could not explain. Newton was aware that his model of gravity was not perfect. He was aware of that. And in there, he saw the hand of God. He just said, I don't know, I guess God does stuff that I don't understand. So yeah, I'm not aware of any time that Newton ever implied that God had made any mistakes or was ever critical of God's work. The level of disconnect there is insane. And even if you're not religious or don't have that sort of connection, how is it acceptable how he uses that explanation to support his theory? It's not acceptable, and I believe that's why dark matter and dark energy are required to keep this model afloat. The level of disconnect here, I think what is the disconnect here is that for some reason you're expressing, and I don't fully understand it, maybe you could explain better why you think this is a disconnect. Newton acknowledged that his model was not perfect. And he left it up to God to make it perfect, right? And our models today are much better than Newton's, but they remain imperfect. It seems like you're trying to say that if the model is imperfect, that we throw it out. And we don't. We do not throw out the imperfect. We use the imperfect, we try to build on it, and we try to improve it. We try to make it better and better over time. And for example, with the story of gravity, Galileo knew a certain bit about gravity and taught that to others. Newton came along and discovered more based on the work of many great scientists who had come in between, and gave us a great new model for gravity that was far, far better and explained much, much more than what we had before that. But Newton was aware, even in his own day, that it was not perfect. He left that to future generations to figure it out. And then it took a long while before much more research was done, and that led eventually to Einstein making his discoveries, which were able to refine the model much further, and Einstein was able to explain things that Newton could not. And that leads us on to the years that go past there, with people like Fritz Zwicky and Vera Rubin making contributions, and so many other people making contributions, that we still know that Einstein's model is not perfect. That doesn't mean it has no value. It does have value. We get closer and closer to perfect as we go. Every time you learn something, you start off with a very rough approximation of what's going on, and then as you learn more and more details and more nuances about that until you become the subject matter expert. And even then, the greatest experts in any field are constantly learning and exploring new things. And that's what science is about. That's how it's supposed to work. I don't think that that's a disconnect. I think that that is what science is supposed to do. So tell me more about why you think that's a disconnect if I have misunderstood you. Question number 5. If there's no atmosphere on the moon, and/or it's not strong enough to provide an inertia reference frame for its spin, then how is it the footage from the moon landing doesn't show any of this movement? Okay. None of the astronauts had trouble jumping off the surface and falling over due to landing on something that's spinning. And keep in mind, they jump in all directions and it never affects them. And there's zero motion on that footage when there should have been, right? Okay, a couple things I want to call out. Number one, a lot of people really struggle with the concept of a reference frame. The reference frame does not come from air. Air does not give us a reference frame. That is not what a reference frame means. A reference frame is just an axis. I'll make you a reference frame. You say that's the x-axis, that's the y-axis, that's the z-axis. I have a reference frame. That's a reference frame. It's a mathematical construct. It is not a physical thing. Okay, so let's keep that clear, and don't invoke that phrase to describe an object or a medium. It is a mathematical construct. Okay, so that's reference frames, but let's go on to the rest of this. There's zero motion on that footage when there should have been. Should there have been? Let's ask that question. And you're asking, you say, right? Well, before we answer that, let's first say, how much is the moon's rotation? The moon is rotating. Yes, it is. How fast? Work that out with me. In fact, if you're watching this now, for Alan or for anybody else who thinks, yeah, what's up with that? I want you to do this. I want you to go through this exercise because this is where you have kind of fallen short in your analysis. The first question you should ask is, what is the rate of the moon's rotation? Just tell me that. How fast is the moon going? Okay, pause it, go Google it, go research it, come back here, and you're going to find the moon goes around the Earth every 27 days. Once every 27.3 days, the moon goes around. And we know that the moon is tidally locked, meaning it's always showing us that same face of the moon. It's always pointing at the Earth. That means that the moon rotates once every 27 days. That comes to half a degree per hour. So you may have heard the Earth goes about 15 degrees per hour. It goes around once a day, right? The moon goes much slower. It goes a 27th of that rate. So it goes only half a degree, 0.55 degrees per hour. And in how do we normally measure rotation speed. Normally we measure rotation speed in RPM, revolutions per minute, and I have that number for you right here. So we need to understand that the moon is rotating very, very slowly. So if you think that trying to stand on something that is moving at half a degree per hour should knock you over or trip you up, then I would say no, you should rethink it, because half a degree per hour is not a lot. Okay, so with that sort of in the back of your mind, and we can debate whether that matters or not, let's ask the other question, which is, what would jumping off a rotating sphere be like? What should happen if we jump off of a rotating sphere? I've got some diagrams here. Let's look at this. Okay, here I have Neil Armstrong standing on the moon, and I put a little line on the moon so we can, give it some detail. We're going to see that rotate. If our astronaut is on the moon's equator, then it is rotating at 4.62 meters per second. Now, here's one of the things that we constantly have as a conflict between the flat earth folks and the globe folks, which is that us globe folks want to describe rotation using a rotational measurement, like revolutions per minute or degrees per hour. These are ways we measure rotations. But the flat earth folks have heard of the linear speed, the tangential speed on the outside, which is much, much greater because of the size of the Earth and the size of the moon. So let's put that up there. The tangential speed for the maximum of anywhere on the moon is 4.6 meters per second. That's how fast the surface is rotating. So we're imagining, here's what's going on. We're going to imagine that our astronaut jumps up, and as he jumps up, the moon rotates underneath him, and then as he falls back down, we see, greatly exaggerated, right? I think we've said this should be half a degree per hour. So in the 2 seconds that he was up in the air, it should not have rotated that far. But in 2 seconds, it will have rotated, 9 meters underneath him, right? So if he was up off the surface for 2 seconds, then 9 meters of moon would move away. And that, I think, is what we're picturing when we describe this scenario. Unfortunately, that is incorrect. I cannot stress this enough. This is not right. Why is this not right? It's because when our astronaut was standing on the moon, they were rotating with the moon, moving at 4.6 meters per second to the right. The moon is rotating, the surface of the moon is moving 4.6 meters per second to the right, and the astronaut is also, he's standing on the moon. He must be moving at the same speed as the surface of the moon. There's no two ways around it. Has to be. If you're standing on the moon, you are moving at the same speed as the moon. So when you jump in the air, you carry with you your upward speed, but you also carry the 4.6 meters per second motion to the right that you started with. There's nothing is going to take that away. There's nothing there to stop your motion. When you jumped off, you jumped straight up. You didn't jump up and backwards, unless, if you tried to, and then that's what you would be doing. You'd be trying to do that. But if you just jump straight up, you carry with you the sideways motion that you started with. So as you come down, you land 9 meters forward, just like the moon has moved 9 meters forward, and you don't even notice that it happened. I have greatly exaggerated the amount of rotation so that we can see it here in this diagram. And it looks like that was a great deal of rotation, and now the astronaut's feet are a little bit up off the moon. So, won't that matter? And now he's not straight up and down anymore, right? He's at an angle. Let's remember what that angle is. that angle is 0.55 degrees per hour. So tell me, how far did it rotate in the 2 seconds that the astronaut was up off the ground coming back down? How far did that thing rotate as an angle? And that'll tell you how much this little angle deviation is. And once you understand that, we don't need to talk about reference frames at all. We just need to understand that when you were in contact with the moon, you had the same speed as the moon. When you jump off, nothing takes that speed away. You can't just take that speed and just say, it's gone now. You can't do that unless you apply some kind of a force to force you to slow down, right? And so, no, it should not be difficult to stand on a rotating sphere unless that sphere is rotating at some really significant speed, which this is not. 0.55 degrees per hour is not a significant speed. The linear tangential speed that you get there is not even noticeable because you just carry it with you. Okay, question 6, the downward vector. There's no denying that when you drop something, it falls to the earth. That's an observable, repeatable phenomena on Earth. I agree absolutely. Yes, tell your friends, bring them on over to the channel, let's talk about this. Yes, you drop something, it goes down, and yes, this is the thing. Then use math to explain things falling around a bend forever and mass attracting mass. Seems like where there's a disconnect. Yeah, I understand. I understand what you're talking about. But let me say it in my words, and maybe you can sort of start to understand my point of view a little bit. I say that the math does not explain things. The math describes things. How is that different? If you've seen my Science for Skeptics series, I try to explain it there, which is we start in the kitchen, we measure some things. We take some measurements and we measure the weight on a scale of different things and buoyancies, and from those observations we can develop an equation. The equation is not an explanation for the measurements. It is a description of the measurements. It says, hey, we measured some things, and this equation describes the measurements that we found. Okay, the math doesn't give us cause and effect. The math just describes the observation. And here's where there is a very serious disconnect here. I had the same problem myself. If you can really read math, and not many people can, it's not anyone's native language. You have to learn that. You have to learn that, and it's like learning a language, and it's a very strange, it's an alien type of language. But if you can read math, as these scientists can do, they learn this. These scientists learn how to read math. And what it does is it can lead you to the explanations. Okay. A quick aside. I know you've watched the video on the video on Michelson-Morley. I'll put that up there. I thought when I was in high school, I thought that Einstein's theory came from some stuff he made up. I thought that Einstein just basically pulled out of thin air certain postulates, like the speed of light is constant for every observer, and Einstein just said that. And yeah, there's a critique for science education there, because that's essentially what I was taught. What I was taught was that Einstein made these postulates, and based on those postulates, relativity falls out. What they didn't effectively teach me was that Einstein looked at what people had learned before him. He looked at Maxwell's equations. He looked at Michelson-Morley. He looked at those things and saw that what they were telling him was that the speed of light is constant for all observers. That not that he didn't just make this up out of nothing. He looked at those descriptions, and what he saw there told him that. And so then Einstein takes those and he puts them into the math, and he uses the language of mathematics to describe what that means. He says, if that's the case, and it appears to be the case, if that is the case, then this math must be true. We can now test to see if that math is true, because we now have a model, and the model makes a prediction. If that prediction is not correct, then that means the math is not correct. If the math is not correct, then what it was based on, that postulate of the speed of light that it was based on, must not be correct. So we go out and we test, and we test and we test and we test, and sure enough, it turns out it was correct. So what am I saying with all this? I'm saying we don't just write a math equation and say that that is science. No, we make an observation. We describe the results of the observation in the language of mathematics, and then that allows us to look at the equation and learn something about the world that gives us a direction to go search. In my Science for Skeptics series, I start with that. I start with making some observations, and then I write an equation that describes my observations. And then the next step I want to take with that is to look at what the math is telling me. And the math is telling me that the difference in density between the object and its medium is crucial to how it's going to behave. But there's this other term sitting there in the math. You can see it in the math. And there's a term, it's a vector quantity, and it comes from nature. It doesn't come from the density of the objects. It comes from something else. This points me in a direction to go and search. What it's telling me, the math is telling me, is that there's a term that has not been explained. It's there. We know it's there. We've measured that it's there. Now the question becomes, what causes that? The math does not tell me what causes it. It tells me what to go look for. And if you can read the math, it tells you what sorts of things to go looking for. Moving on, there's more to this question. They're making assumptions and then reverse engineering it back to an observation on Earth and saying that because things fall to the ground, all these things in the sky are in a perfect game of tug of war based on their mass and velocity around a relative curve that can't be measured unless it's through a telescope looking at something that's allegedly hundreds, sometimes thousands of light years away. Only then can you see this relativity effect bending through gravitational lensing. Okay, I hear you. I feel where you're coming from. I understand the frustration with this. Let's just back up a little bit and let's boil it down to what we've really got. It's a lot. It's a huge pile of stuff that is dumped on you all at once, and that, I firmly believe, that is a big part of the problem. Big part of the problem is trying to understand things like dark matter, dark energy, general relativity, all those kinds of things before you've really come to grips with what Isaac Newton knew, and that maybe is even before you've come to grips with what Galileo understood. If you jump straight into the deep end, let's start in the shallow, right? Let's start in the shallow end, learn a few things, and build from there. Well, let me summarize it. What you've said here as we have observations from many different kinds, and some of them here, right here on the ground, some of them are up in the sky, things that we observe. We have lots and lots of different observations, all sorts of different observations. What we're doing with this science stuff is trying to search for the rules that explain these observations. Brahe made these observations, Kepler looked at those, and wrote a mathematical formula that described those observations. Newton looked at that mathematical formula and he said, that tells me that there's a force here. Let me mathematically describe the force. That's what he did. He took the observations that they had made and described it mathematically. And then, yes, you are right. He took that model that he had built and applied it to here on Earth and said, what would that mean? If that were true, what would that mean to us here on Earth? And discovered that, yes, it applies. It applies to our everyday things. Ice cube in a glass of water in your kitchen can be described by the same formula that was derived from the elliptical motion of the planets. And that is a wonderful and beautiful thing. Sometimes we find amazing connections between the motion of the planets and the weight of an ice cube in your kitchen. I'm excited about that. And then when you go and look for an actual picture of something taken using gravitational lensing, all you get are animated CGI graphics and stuff. And
CGI.
Is that the case? I don't agree with that. I think that I have seen images, actual images. Let's take a look at one. Right here, here's a link. Again, I get that down in the description for you. So here we have that Hubble image. This is not a CGI, or at least, maybe you could say, you think that CGI. They don't say it is. So the people who offer us this photo say that this is a genuine image taken by the Hubble telescope in which we can see the effect of gravitational lensing taking place. We can see these stretched out sort of curved shapes that occur, and the repeated images of things at different angles that happen as they go around the lens. They tell us that it is not an animated graphic, it is not a CGI. They tell us that these are images taken from the Hubble telescope. Question 6C. If the sun's size and distance are correct, and the sun is 8 light minutes away, if you double the distance and half the size, you have 16 light minutes. Keep doing that, and by the time you get to a light day, the sun has gone from the sky. Okay, forget about a light year. So just working out that distance with what's alleged and what we can see. How do we see light from an object that's allegedly hundreds of light years if we couldn't even see our sun at one light day? Okay, good questions, good thinking, but where you've stopped short again is answering the obvious questions that you have posed. You seem to have jumped straight to your own personal answer to those questions without ever asking the questions. The questions I would ask, exactly how small is too small to be seen? And if something were smaller than that, whatever's too small to be seen is, when something gets smaller than that, what would you see when you looked at it? This is a very common problem. I'm gonna have to do a whole video dedicated just to this one because this is a really good question. People don't know, and there are a lot of big misconceptions about this. So let's answer the question, what is too small to see, and what happens if something is smaller than that? I'm going to imagine here a CCD camera, right? The way a CCD camera works, it's got little pixels in it that when light hits that pixel records the color of the light that hits that pixel. So I'll make a very small CCD that's just 8 by 8, an 8 by 8 grid of pixels. You might say, okay, what if it's not a CCD? What if just my eye? Your eye works in a very similar way. There are receptors, cells at the back of your eye that sense light, and each cell will sense light individually, and we make out a detailed image because there's lots of those cells. It works very similar to this. Okay, so let's say this is the sun. We're going to take a picture of the sun using our CCD camera. So we line up our camera so that the sun is, the image of the sun is hitting that CCD. So what happens is we pixelize the image, right? We turn the image into pixels. Each pixel that is hit by the light of the sun changes to that color. And that's what we see there. So we get a pixelated version of the image of the sun. So that's what a big sun looks like. Let's push that sun away. So here we have a far distant sun that is much smaller visually. And what happens when we take the picture of that? Well, this sun is completely filling this pixel right here in the middle and only just barely touching the pixels on the side. And so when we pixelate that, we get an image like so, where now the sun is reduced to just one pixel and maybe a little bit of overlap onto some pixels near it. Let's make the sun a teeny tiny little speck. So a teeny tiny little speck that is now much smaller than the pixel that the camera can possibly see. What are we going to see when we take this picture? Are we going to see a completely black image? No, because all of the light from the sun hit that one pixel. It did hit the pixel. Even though it is smaller than the pixel, the light from that object still hit the pixel. And because of that, we'll get a very dimly lit little pixel, a single pixel. And we can keep pushing that away and make it smaller and smaller and smaller. It cannot get any smaller than one pixel. So as far as physical size, the physical size of that object cannot shrink anymore for this camera. In order to get a better picture, we're going to need a better camera than this. But with this camera, there's nothing smaller than a pixel. And when something is smaller than a pixel, that does not mean it's invisible. That means it just looks like a pixel. It looks like a pixel, and it gets dimmer and dimmer and dimmer. It doesn't get smaller and smaller anymore. Once it's at the size of a pixel, it cannot get any smaller, but as you push it away, it will continue to get dimmer and dimmer and dimmer. Now you might ask, okay, but then isn't it too dim to see? If we keep going, it's going to get dimmer to where we're not going to see that anymore. And yes, it'll keep getting dimmer and dimmer and dimmer until you can't make it out with this camera anymore. There's no such thing as too small to see. There is too dim to see. Too dim to see would be where there's a single pixel here, but I cannot make it out against just the background noise of just random light scatter in the environment. I cannot tell the difference between that and something else. And yes, that absolutely does happen. You might ask, well, okay, how far away does a star need to be before you can no longer see it? I can edit that here. I looked up for you the distance to the stars that we can actually see with the naked eye, and here's a reference. I will, as always, throw that down in the description for you. But what do we find? The closest thing that you can see, the closest star, is 4.3 light years away, and the farthest single star you can see with the naked eye is about 4,000 light years away. And you can only see that one because it is a supergiant that is incredibly bright. Yeah, and so that's interesting. We do talk about hundreds of thousands of light years. In fact, the Milky Way, yeah, right here, the Milky Way is 100,000 light years across. That means we cannot see the stars over there, not with our eyes. We're going to need, some high-powered telescopes to see those distant things. You can see the other things that you see out there might be larger than a single star, like galaxies, stuff like that. Because you raise some commonly asked questions, some good questions, some things that I do have thoughts about. The camera thing, maybe I'll make a whole separate video for the idea of what is too small to see. because there are some very strong misconceptions out there about how cameras even work, or how eyes, the human eye works. The message I want to deliver is that scientists don't just make up stuff, and we don't just accept it when something new comes out. That's not how this is supposed to work. It's supposed to work in that we take the observations of people who've come before us, we add new observations to that pile, and we do build models of what we've seen. That is very much a part of the scientific process. And then we try to see if that model applies to other things. Yes, that's what we do. That is what we're trying to do, right? We're trying to make a simplified way of looking at all of this data that we've collected. And when we find something that seems to work, then that is not in itself the explanation. The model is not the explanation. The model is a model. It's a simplification of what we've observed. And because of that, there's a couple of things to understand about that. The first thing is, it is a simplification. If the model is not simpler than the data we gathered it from, then there's no point. It doesn't have any purpose. The model is a simplification, and so because of that, we expect it to be incomplete. We expect it to not catch every single little nuance. And we will continue to look for refined models that do catch those nuances. So that's why we don't throw out a model when it's imperfect. We understand that it's not supposed to be perfect. It's supposed to be useful. Okay? And so when you hear somebody say, we don't believe in Newton's gravity anymore because Einstein came along and just destroyed Newton's thing. No, Newton had a model that is not perfect, but it remains very, very useful. And so we'll keep using it. Einstein's model is more refined, but harder to use. So we'd use it all the time if it wasn't so difficult to use, but it is. It's very difficult to use. So we're only going to bust that thing out if we really, really need that extra level of precision. And we know that Einstein's model is not perfect. There are a number of ways that we're already perfectly aware that there's something more coming past Einstein. We just don't know what that is yet. And we're all waiting to see what the next great step is going to be. So the other thing about those models that I want to express is that the models don't explain what we're seeing. They describe what we're seeing. But looking at the model, you can get clues as to what the explanation might be. And that gives you places to go and look. Like Vera Rubin had a clue from Fritz Zwicky before that maybe the rotation rates of galaxies would not match the gravitational model that we have, and so she went and she measured it to find out. The model and the holes in the model that had been discovered gave her a clue of what to go looking for. So she went and looked for it. And now we all know her name because she's famous because she made a discovery of something that we didn't know before. So we don't simply take her word for it because she's a famous scientist. No, she's a famous scientist because she made a discovery that people did not know before, but people since have verified was correct. And so that's where we stand. Hopefully that was somewhat helpful. Super, super long. I'm going to have to get into the editing room and see if I can trim this down into something usable. Okay. Looking forward to talking to you again soon, particularly Alan. I want to have you on. We'll do a live discussion about this type of thing. We can do some back and forth about this. See you all in the next one.